course, you're welcome to this session of online teaching. Some people are going to watch me as a recorded teacher, which has no problem. So today we are for physics, and that is A-level physics, a concept of simple harmonic motion. So my local students, the international students of Cambridge, EDXL, AQA, this is your physics tonight. The mathematicians who are watching me today, oh, don't go away. Even if you don't offer physics, this is a topic you need, which is part of mechanics, of mathematics. And you need also to hear this today, that the topic I'm introducing in physics today was discovered by a mathematician, a French mathematician, by names of Joseph Fourier, a French mathematician, in 1822. If we can go into the history, that is 1822, by a French mathematician by names of Joseph Fourier. So, what is simple harmonic motion? We need a definition for it. Then also, why is it called simple? Oh, that is now your assignment. Why do we call it simple harmonic? Oh, but by definition, we are going to discover today that simple harmonic motion is an oscillatory motion. Oh, I know people had different definitions, and this is the reason why I'm here today. I've come to tell you what is considered in the marking. I've not said periodic, but I'm talking about an oscillatory motion, whose acceleration is directly proportional to the displacement from a fixed point. And the acceleration is towards that particular point. What am I trying to mean here? We can go and demonstrate. If we have a linear kind of simple harmonic motion, we are going to see that simple harmonic motion is of two types. We have what we call linear simple harmonic motion, and then what we call the circular simple harmonic motion. Those are the two categories, or the two types. Now, if we are looking at linear, assuming I have a point here, and this is a point Z, and this is Z prime, okay? And then we have what we call a mean position, assuming this is an oscillating body, which is going to be on a particular path, okay? Assuming you have tied the rubber band here, and at this point, and you have put a particle, its mean position is this, and then finally it is moving along the rubber band. It's moving along the rubber band, or it is a spring, for example, because we are going to see those are some of the items where simple harmonic motion can be observed. Now, assuming this is a mean position, and I'm calling it O, I have my particle which has moved from a mean position. When I talk of mean position, I'm referring to equilibrium and equilibrium position. So a particle at this point is moving away from the mean position towards Z prime. However, we are going to observe that as it moves with its velocity towards Z prime, the acceleration of this particle is directly towards the mean position, which means the acceleration of this particle is provided by a restoring force. There is a restoring force. The restoring force is towards. Why is it a restoring force? As this particle moves towards Z prime, its speed reduces, and it is momentarily at rest at Z prime. So meaning that at this point, we will not expect it to accelerate. But again, we are seeing it moves back with an acceleration, which means there is a restoring force trying to pull the particle towards the mean position. And as a result, it even bypasses the mean position and goes up to another maximum displacement. As it reaches the mean position, the acceleration becomes zero. So at this point, acceleration is zero at mean position. But once the acceleration is zero, automatically the restoring force is is also 0. So this is the equilibrium position, and it is a fixed point. It is a fixed point. So what are we trying to see now? We are going to see that the displacement from the mean position up to where the particle is at a time t is what we are calling the displacement. And since we are dealing with the linear horizontal, we can give it x in reference to the x-axis. So this is displacement of x. Okay, now if the particle is maximally displaced up to a maximum point such that there is a maximum displacement, then that maximum displacement is what we call the amplitude, capital A. So this is amplitude, the maximum displacement of the particle from its fixed position, or from the equilibrium position, or from the mean position. When the particle bypasses the mean position and gains another maximum displacement up to point Z, or you can call it Z, then we are going to see that the distance ZO is also amplitude A. This is also amplitude. So what are we saying? We are saying that a simple harmonic motion is an oscillatory motion. We are going to see the difference between oscillatory and periodic. I know some people have been defining it as a periodic motion. We are going to discover today that all oscillatory motions, yes, they are periodic, but not all periodic motions are oscillatory. Oh, that is very interesting. I don't know that you are noting out these words. Now, the acceleration of this particle in simple harmonic motion is directly proportional to any displacement of the particle from the rest position. So A is directly proportional to x. However, we are seeing, or we are observing, acceleration and displacement. They are all vector quantities, but they are not in the same direction. The restoring force is towards the mean position. The acceleration is moving towards the mean position. And again, the body is moving away from the mean position. Its displacement is off from the mean position. So, which means the acceleration is going to be negative because of now the direction of the displacement being different from that of the acceleration. So when we remove the sign of proportionality and introduce equal signs, still we are going to introduce a negative sign and a constant of proportionality. So we are going to see that A, okay, is now becoming a negative kx. So this is a constant of proportionality. But now we are going to observe that as a body moves to and fro, by passing the mean position, to and fro, from one end to the other end, oh, like a guitar. People who have ever struck a guitar, a violin, okay, rubber bands, if you stuck them, the pendulum of the clock. These are the real life applications of simple harmonic motion. The hearing process, the casual absorbers, oh, swings in parks where people go and have fun. If you have ever gone to a park, the swings which are there, oh my dear, it is kind of simple harmonic motion. So the topic I've come to introduce today is not abstract. It is a real topic which we find in real life. Oh my dear. So we are going to discover today that as a particle moves to and fro, it is describing a particular kind of motion which is an ellipse, in an ellipse form. So it is an elliptical kind of motion, meaning that a body is moving with an angular frequency. There is an angular frequency. If a body is displaced from a particular point, as we shall see in the case of such cyclic or circular simple harmonic motion, we are going to see that at a time t, assuming this is the horizontal position, when a particle is displaced, it moves through a particular angle. And we are going to see this angular frequency is the rate of change of the angle with time. So we need to talk about angular frequency. So it was discovered that the constant k is an angular frequency squared. It is the square of the angular frequency. So we finally now get A as negative omega squared x. Omega squared is the angular frequency. So we are coming to all this. This has been just an introduction. Immediately after a break, I'm coming back with the real life application, and then the topic outline, and we start off with simple harmonic motion in a very, very simple way. Stay tuned. Break, the still teacher, Sulait Sabaiga. So we are saying that the topic we have introduced tonight is not abstract. It is applied in real life. For example, it is applied, I've already talked about the pendulum of the clock. The pendulum of the clock. You can go and expand the thinking. I will just outline the applications, then you go and make more Google searches about these applications. Talk about the guitar, when you start the string of the guitar. So in musical instruments, most of the musical instruments, the guitar, the violin, all those use this topic of simple harmonic motion. The bungee jumping, oh my dear. Rubber bands, talk about diving boards, talk about earthquake. Yes, I have simple application. The live example is an earthquake. Oh, swings in parks, I've already talked about them. Car shock absorbers. Oh, motorbike shock absorbers. They execute. We are going to use this word, execute. They execute simple harmonic motion. The hearing process, I've also talked about it. We are going also to see execution of simple harmonic motion. So let us go, give the definition, and then talk about the topic outline. For people who need to write, this is the definition. So definition. Simple harmonic motion is an oscillatory motion. Whose acceleration is directly proportional to the displacement from a fixed point. Which fixed point is the mean or equilibrium position. Along any path. And it is directed towards that point, meaning the fixed position. So that is simple harmonic motion. So, i.e., we are seeing that A is directly proportional to the displacement from a fixed point. And then A is equal to negative kx, where k is equal to omega squared, the angular frequency. And then A is the acceleration, whereas x is displacement. Displacement from fixed point, from the fixed point. So we can now conclusively say that A is equal to negative omega squared x. We get this from the definition. Acceleration is directly proportional to displacement from a fixed point, and it is directed towards that fixed point. So what we need to note here today, we need to note the marking points here. Oscillatory. We need to talk about oscillatory, not periodic. As we have already said that not all periodic motions are oscillatory. However, all oscillatory motions are periodic. We are coming to see the difference between oscillatory motions and then periodic motions. With time, we are going to talk about that. So, you need to note the word oscillatory, it has to be there. Then acceleration being proportional to displacement, okay, from a fixed point. You need to talk about a fixed point, and also being directed towards that point. So that is the definition of simple harmonic motion. Now, let us talk about the course outline. What are we going to talk about in this concept, or the major things inside? So that gives us the course outline, or what we call the topic outline. The topic outline. So, dear viewers, we are going to talk about definition. We have already finished it. Now, we are going to talk about, first of all, the characteristics of a simple harmonic motion. X-sticks. Characteristics of simple harmonic motion. Then we are going to talk about generally on the acceleration, which we have already done. So acceleration of a simple harmonic motion. Then from there we shall talk about the speed. But we have already talked about displacement. You can also bring it, like acceleration and displacement. So speed, or what we call the velocity of a simple harmonic motion. So I believe that today, or by this level, you know the difference between speed and velocity. With velocity, vector quantity, direction is considered. Then speed in a given direction is also velocity. So we are going to see how to calculate this speed. Calculation of speed of a simple harmonic motion. Then we are going to talk about characteristic graphs, or what we call the simple harmonic graphs. Simple harmonic graph. So we are going to also see that in this topic of simple harmonic motion, energy is being conserved. So we are going to talk about the energy in simple harmonic motion. Energy stored in different strings, energy stored in the springs, and how this energy is conserved. So energy in simple harmonic motion. Yes, for people who are doing physics at AQA, then you can add on some the oscillations majorly. Yes, you can talk of the damped oscillations, actually damping. You add on that damping. But what I want to cover with my local students, it is this: characteristics, acceleration, speed, calculations of speed, and then characteristic graphs. Did I talk about them? Graphs. You need to note this. You need to note the course outline such that you are very, very aware of what we are going to talk about. So graphs. This was graphs in simple harmonic motion. So immediately after this coming break, we are now coming with the very, very first topic outline. Those are the characteristics of simple harmonic motion. Stay tuned.